here already attending. Let me hit the go live in the YouTube stream. Fine. Everything is streaming.
Yay.
Okay. Okay, so welcome everyone to this new event of the Barcelona JAG. And now we have Dinakar that is going to show us how to right size or how to optimize our Kubernetes cluster. But first of all, I need to give a brief introduction of what Barcelona JAG is and what we do and which are our next and past events. So I'm going to share my screen. One moment, please. Okay. This is no, this is not. This is. Let me. I'm not finding. Why?
Oh, I have to stop sharing or?
No, I already stopped you from sharing.
Okay.
Is this one? Am I sharing the right one? I'm not sure. I don't think I'm sharing the right one. Recently, I upgraded my Fedora, and I'm wow. Now I cannot find my. Sorry, I will do it another way. Sorry, but now I cannot share. Okay, let's do it in a third approach. No, it doesn't allow me to share. Okay, I will share my presentation at the end.
Okay.
But you can start. Sorry, I will share at the end because now I don't know what is happening and I cannot share my screen. So go ahead, Dinakar, and yeah, the stage is yours.
Okay. Yeah. Thank you, Jonathan. I'd just like to thank everyone for attending today. I know that Christmas is just around the corner, so I really appreciate you taking the time to attend this session, and also like to thank Jonathan for inviting me to speak at this session. Today I'll be talking about optimizing application performance on Kubernetes, but I'll be emphasizing Java here because obviously I'm speaking to the Barcelona JAG. So a little bit about me. I'm a runtimes cloud optimization architect at Red Hat. And part of my job is to optimize applications specifically for Kubernetes, as well as I help customers move their legacy applications to the cloud. I also help maintain the AdoptOpenJDK community Docker images as well. So in India, we have a common saying, it's called "Kitna deti hai." It's like, what's the mileage? So this is commonly something that we ask when, let's say, we are buying a car or a vehicle or something like that. And what I've noticed is that these days, customers are starting to ask the same question about Kubernetes. More and more people are adopting Kubernetes, and now they are trying to figure out how best to tune the system so that they can get the most mileage out of the system as well. So just let me take a moment to define what I mean by performance. So traditionally, performance looks at three key aspects: throughput, response time, and utilization of the system resources. So these are the criteria that we will be looking to optimize in today's presentation as well. However, I just wanted to make it clear that I'll be confining myself only to compute optimization and not necessarily anything to do with networking or storage. One other thing that I just wanted to mention was, depending on where your Kubernetes cluster is deployed, you might have a different set of performance tuning knobs to play around with. For example, in private clouds, they offer a lot more controls and tunables owing to the fact that the IT admins have physical access to the hardware on which the cluster is running. However, on public clouds, on the other hand, they are mostly preset controls, and so they offer a smaller set of tunables when it comes to the hardware itself. So I've used these two controls that I've depicted here to determine whether a particular set of tunables are applicable, where a particular set of tunables are applicable throughout this presentation. So if you see, this icon, then the tunables that I'm talking about is applicable to public cloud, and if you see this one, this is applicable to private cloud. And if you see both of them, that means it's applicable everywhere. So that's how it's going to be. So the first thing that I wanted to start off with is what I'm trying to do here is to start from the build process. So if you are an application developer and you want to get the most out of your application in which is going to run in Kubernetes, you start right from the build itself. So in the build phase itself, it's very important that you produce what is called as a Kubernetes optimized container image. So what does that mean? So essentially, we want to try and produce the smallest image possible because the smaller the size of the Docker image or the container image, it affects the provisioning time and the deployment time, as well as it's important from a security perspective as well. So if you look at a small-sized images, they have lesser attack surface, and so it's good from that perspective as well. So what are some of the options that you can look at? There's something like Alpine Linux, which is really small, 5 MB in size, versus 80 MB for Ubuntu. There are lots of the images, like for example, Java has a slim variant. And of course, if you're specifically talking about Java, then we have something like JLink.
Dinakar,
yeah.
Dinakar, one thing, are you sharing your slides?
Oh, I'm so sorry. I think I...
No, I thought you were doing an introduction, but okay.
Oh, I forgot that the screen share stopped when I...
Yeah. No, was my fault. Sorry.
No, that's okay. Sorry. Yeah. So I think I just... Okay, then let me just quickly talk about this. So what I was saying was basically... So when I mentioned that I have these two icons here, so I hope you're able to see my screen, right? So you're Jonathan, you're able to see my screen?
Yeah.
Okay.
We can see
sorry.
the screen. Yeah, sure.
Okay. So what I was talking about earlier was these two icons. So this one is for public cloud, and this one is for private cloud. And if you see both of them, that means those tunables are applicable to all the, both the clouds essentially. So this is what I mean, for example. So in this slide, I have this at the top right, which means that this is applicable to all kinds of clouds. So what I was saying was that the first step is to try and produce, right at the build phase, to try and produce the smallest possible image size. And this has an effect on the application provisioning time and the deployment time. And there are slim variants which allow you to, for example, Java has a slim variant, and the operating systems themselves, so like Debian has a Debian Slim and so on. So this has a smaller subset which is only applicable for applications which are running in the cloud. And so I think that is something that I would encourage you to use. Of course, if you're running a Java application, it's always better to use JLink to come out with a custom JRE. So rather than just talk about it, I have here a Docker file that can help you to get the smallest possible image for your application. So just for your reference, this entire, these Docker files are available here publicly on github.com. So dinogun, this is my GitHub ID. And Watson-Spring Boot is the application that, this is just an example application. And I have some of the things that I'm talking about are available here as well. And specifically today, I'll be talking about this particular Docker file, which essentially has all the stuff that I'm just going to be going through. So in this particular Docker file, if you see, this is actually what is called as a two-stage Docker file. So you have the build phase, build stage, so which is the first stage, and then at the bottom here, we have the runtime phase, which is the the second half of the Docker file. So these two phases are optimized for different things. So the build phase has been optimized to add as many layers as possible so that you get the fastest possible developer build time. So when you're developing an application and you're trying to build it, you don't want the build to take too long. So you want to use the caching that's available with Docker to try and complete the build as quickly as possible. Whereas in the runtime phase, you want the smallest possible image with the least amount of layers so that the deployment can happen really fast, and the startup happens faster as well as a result. So if you look at how to optimize on the build time, essentially, the first thing I would suggest is use a publicly available image like the Maven image, instead of having it installed locally on your system, simply because you get the you get all the updates, including operating system updates and things like that. And any build fixes for the tool itself. So using a tool, Docker image actually helps a lot. And if you're aware of how the Docker file works, every single line in the Docker file represents a caching layer. And so if there are no changes in that particular layer, for example, if you do a git clone and there are no changes, that means essentially it's going to reuse the previous cached image and not have to redo that particular step. And so we can take advantage of that by doing something like this, where you can install all of the application dependencies using the copy dependencies option of Maven. And most of the times, dependencies don't change all that much. So this means that all of your dependencies are downloaded only one time, and your build happens faster. And of course, this step is where you would actually do the build. The next thing is best practices to create a non-root user, because you don't want to be running as root, because that gives additional privileges, which you don't want to when you're running inside of a Kubernetes cluster. And so it's ideally best to create a non-root user and switch over to that user for the rest of the commands that you're doing here.
Dinakar, I have a question
Yeah.
about the layers on
Yeah.
your Docker image, well, container image.
Mhm.
Is that something, if I'm not wrong, this is something that already Jeep is doing, that is separating the layers, and your dependencies are put in a separate layer. Therefore, only your code is in a specific layer and not all the dependencies. Therefore, it will be faster, and whenever you push and pull um, an image. Is that
Correct.
right?
Yeah. Yeah. Absolutely. Yeah. So what I'm saying here is, how to write your Docker file in such a way that you can make use of these layers. So, for example, if you remove this step, if you remove this particular step and try to do it in, install the dependencies as well in this step itself, you're not using the layering concept, and so you'll end up downloading the dependencies every single time you make even a small change. So that way you're making use of the Docker layering concept, and making effective use of the Docker layering concept. That's what I'm trying to say here. I hope that is clear.
Yeah, thank you.
Okay. Okay. So once you switched over to a new user, the next step is you can use JLink to create a custom JRE. So one advantage here with JLink is that you really don't have to have a modularized application. So even if you have older application, legacy application that has not been modularized, you can still use JLink to produce a smaller JRE, which is a custom JRE, which is only applicable to your particular application. The only difference between a modular application and a non-modular application is that for a non-modular application, so for example, the current application that I've written this Docker file for is actually a non-modular application. So I have to manually specify all of the modules within the JVM that are specific to my application. However, if my application was modular, then just this particular step using JDEPs and providing my jar, it would automatically resolve all of the dependencies and add all of the modules that are required. So at the end of this step, I'm going to create a custom JRE that is specific to my application. And the next, again, this is a best practice. This is specifically applicable to OpenJ9 JVM. But the rest of the steps I just talked about, they are common to Hotspot as well as OpenJ9. So in this particular case, there is, OpenJ9 has a concept called as the shared class cache. Basically, this is the AOT code. So what happens here is that I'm actually running the application within the application that was just now built. So when I run this application, it actually creates the AOT code when it is running for the first time. And so that creates a AOT code in a special file, which is called as the shared class cache file, and it will be copied to this particular directory. So the next time you run this application, it will start up much faster because it already has the AOT code, which will help it to start faster. So this completes the build phase, essentially. And now we have the second part of the Docker file, which is the runtime phase. So this one, as you can see here, will have lesser number of layers because here the whole point is to have the smallest possible Docker image that can be deployed. So here I'm starting off with the Alpine image. So this is a special Alpine image that I've created because Alpine by default has muscle libc, and the JRE that we have built uses glibc. So what I've done here is created a custom Alpine image that has glibc installed on top of it, but this is still very small. It is about 17 MB in size. So 5 MB of the base Alpine image plus about 12 MB of glibc. So it's about 17 MB in size. So then the same thing that I did earlier. So I'm creating a user and switching over to that user. And here you see, for example, if you're using any of the Eclipse microprofile related frameworks, whether it is Quarkus or Liberty or any of this, they actually separate the dependencies and produce what is called as a hollow jar. So this is the application jar, and so I'm copying that separately, and these are all the dependencies. So these dependencies, I don't expect them to change all that often. So we copy the dependencies first, and so all these steps, till this point, they usually will not change at all. So these are all cached, and they can be reused from the previous build itself. So when you do a new build, probably this is the only thing that will change. And then, of course, the shared class cache that we produced, which was copied into the temp SSE folder. So now this gets copied onto the Docker image as well. So we have the dependencies, we have the application itself, and we have the shared class cache, which we just built. So
another question.
Yeah.
Recently in our project, well, I was not aware of this type of packaging, but I found these shaded jars that include all the class files in a fat folder. Yeah, but not the jars, only the .class elements. So do you recommend or you don't recommend this approach in terms of performance?
Well, from a performance perspective, yes. I mean, having the .class files does make sense. As in, I guess it is something like it's a one-time task that happens at JVM startup where you're loading all these classes, and that's where the shared class cache comes into picture. Or in Hotspot we have something called a CDS, right? Class data sharing.
Okay.
So if you use class data sharing in Hotspot or shared class cache in OpenJ9, that will bring down the startup time. Essentially, the load of the application is where you are going to be loading all those classes, and if you have it in a jar format, it has to unzip it first and then load those classes. Whereas if you have it in shared class, if you have created the shared class cache, then it has close to the peak assembly level code, and so that helps it to start up really fast. So yeah, using class data sharing or SCC actually alleviates this aspect where it doesn't really matter if you're storing it as a jar or individual class files. Okay. So yeah, so I think that's so this is pretty much all about how to make sure that you have built the smallest possible image size. So I have a few set of so all the Docker files that I just showed here, which has all these different options with Java 8 and Java 11 and Hotspot and OpenJ9. So you can take a look at this depending on which particular variant that you are using. So I just wanted to show you how Java 8 and Java 11 compare when it comes to the size of the image itself. So if you see here, this is the image that I was talking about, where we are creating a shared class cache with a JLink option. So this, as you can see, is about 129 MB in size, and this is, of course, with Java 11. So if you see the corresponding Java 8 image, the full image is actually 287 MB in size. So this is more than double that. And even if you use a slim option, that is still bigger. So if you don't have the shared class cache, in fact, you can make it even more smaller. The Hotspot image is actually just about 97 MB in size. So So the advantage with this image is that not only is it small, but it also helps you to start up faster. So adding the shared class cache helps you to start your application by about 40% faster. So for example, the normal app, if I run this this one, which is just the JLink option, it takes about 5 seconds. Whereas with this one, the startup is about 3 seconds. So it's about 40% faster with this option. So that means that once you deploy to the Kubernetes cluster, you get faster startup by up to 40%, not only when you're starting the application for the first time, but whenever you're scaling the application, the newer instances get started up 40% faster as well. So that's the first aspect that we need to keep in mind. And the second aspect, a common mistake that a lot of Java programmers do, is to hard code the size of the heap. So typically what happens is people use the -xmx and xms options. Unfortunately, this is not good in a container environment. So I mean, here the figures illustrate why it is not good. So let us say, I mean, one of the things with Kubernetes is that Kubernetes sets limits to a container. So you can set a limit to a container saying that it cannot go beyond this much amount of size for the entire container. Like for example, here are three application instances, the same application instance that has been started with different container limits. So this one has been started with 2 GB limit, this one is 3 GB, and this one is 4 GB. So if you have hard-coded the XMX and set it to 2 GB, in this particular case, it might actually end up crashing the image, because if you occupy the entire 2 gig, then you don't have any space for your native memory, and so this might actually end up crashing your container. But whereas in this particular case, it might work fine. Whereas in this particular case, you're essentially wasting memory. So you have set the heap size as 2 gig, whereas your container limit, you can actually use up to 4 gig. So you're wasting 2 gig of memory, assuming that you don't need that much for your native memory. So a better option instead is to use -xx max RAM percentage. So the first thing to note here is that all the recent JVMs, starting from in fact Java 8 onwards, they're all aware of containers. So it's called as the Container Aware JVM, and so there have been new options have been added called as the max RAM percentage and initial RAM percentage, which replaces the XMX and XMS. So the advantage with this is that this creates the size of the heap as a percentage of the limit that has been imposed on the container. So for example, if you set max RAM percentage as 80, then automatically the size of the heap will be set to 1.6 GB, sorry. In the case of 2 gig, for 3 gig, it will become 2.4 gig, and for 4 gig, the heap size will become 3.2 gig. So it can automatically set the size of the heap based on the container limits that have been imposed onto the container. So I would really strongly suggest that you use max RAM percentage and initial RAM percentage, and please don't use XMX, because that can cause either your containers to get killed or you're hoarding resources. So both of them are really not ideal situations. So the next thing, and here, this is the most important aspect, is to right size the container. So, what do I mean by this? So the thing here is that if you look at a YAML file, which is a common, which is a typical YAML file that we can use to deploy any particular application. So in this particular case, it's the Acme benchmark application. So here we are specifying what are called as resources, which tells Kubernetes how much resources have to be set aside for this particular application. The issue, if you don't add this part, is that Kubernetes will treat it as a best effort QoS class. So what that means is, There are no guaranteed resources that are being set aside for that particular application. Which, what I'm trying to say is, if you don't specify this part, the resources part, then Kubernetes treats it as a best effort QoS class, which means that your performance can be affected very badly because there are no resources that have been set aside for your application pod. So there are two other QoS classes. One is the guaranteed and burstable. Guaranteed is where both the request and limits are the same. And burstable is where you have requests, limits which are higher than the requests. So what exactly are these values? So requests are guaranteed resources. So if I have said this application pod requires 2 cores and 500 meg of RAM, so that means Kubernetes finds a node where at least this much amount of resources are available and sets it aside so that nobody else can use these resources. So these are set aside only for this particular application. And the limits here, if they are over and on top of the request, they can be used to handle any spikes. So if you have a certain GC activity or maybe a new incoming load which you had not anticipated, so those kind of things can spike the CPU momentarily. And so limits are usually to handle those kind of situations where you don't want the pod to be killed, but you want to set aside enough amount of request resources so that your performance, your performance is primarily handled by this part. How much of guaranteed resources are available? So limits only will handle spikes. So if you keep this in mind, we should always try to use the burstable QoS class because this gives you the best possible performance. Another aspect that you need to be aware of is the use of limit range. So usually Kubernetes admins set up a limit range so that one particular application does not take up too much of resources. So the admin might have said that for this particular, let's say, a namespace, it can be specific to a namespace or it can be specific to a cluster. It really depends on what particular aspect that this has been applied to. So, for example, if it is applied to a particular, either a container or a namespace or whatever it might be, so this will limit it to just one CPU and 512 meg as the default. And if nothing has been set, then it can be even lower than that. So if you're trying to set something higher, this might not work. So you need to be aware of if there are any limit ranges set so that they don't come in the way of whatever application has been deployed. So the next question here is, so we know that we have to set limits, and setting limits is the best practice, and the Java heap can set itself autonomously based on how much limit has been imposed. But the question here is, what is this value? How can we arrive at this value? How can we arrive at what is the right value for the request and for the limits? So there are some tools that come with Kubernetes. The first one is the horizontal pod autoscaler. So this comes with Kubernetes, and there's a kind called as horizontal pod autoscaler. But actually, I would I would actually suggest that you use Cruise, which is a tool that we are working on, and I'll demo that in a minute. But we will look at other aspects as well. So there is something called as a virtual vertical pod autoscaler and a cluster autoscaler. Again, these are best practices to ensure that you get the best possible performance of your application. And the way these things help here is, so if you look at a vertical pod autoscaler, I'm sorry. I said it wrong. So vertical pod autoscaler is the one that I said that you don't have to worry about that, and I'll talk about Cruise. Horizontal pod autoscaler is something that is used to scale your pods on a horizontal basis. Basically, at what point in time should you start instantiating new application instances. So that is governed by the horizontal pod autoscaler. So typically, one of the issues that I've seen where IT admins do a common mistake is they tend to use the most common horizontal pod autoscaler principle, which is, so if the CPU goes beyond, let's say, some value, let's say average CPU utilization goes beyond 50%, then start a new instance of, and here this particular YAML is saying that, as soon as you cross 50, you can start a new replica and you can go up to a maximum of 10 replicas. The problem with this approach here is that you can actually trigger the average CPU utilization for all kinds of reasons. So, for example, if there is a lot of JIT activity in the background or a GC activity, that might trigger your average CPU utilization to go beyond 50%, and that might start a new instance, which might not be really ideal. So the better way to do it is to actually use app-specific metrics. So, for example, you can set the horizontal pod autoscaler based on requests per second, for example. So this means that if the requests go beyond a certain values, for example, 10K in this particular case, then it will start a new instance, which is probably a much better way to horizontally scale rather than just using CPU utilization. The other aspect to look at HPA is...
May I interrupt you here? Just for me to recap and understand, because you said something that I never thought before, but I think it's very important. So if we set the horizontal scaling based on CPU consumption, it could be that the garbage collector makes the CPU to ghost high. Then we create another pod to do absolutely nothing, just because we were just simply removing things in our pod, and probably without any request going on. So that would mean, depending on where you have your cluster, it could mean paying for that extra pod. And if you don't have a scale to zero or downscaling properly set, then probably you are wasting money just because your garbage collector started. Yes. Okay, that's very, very interesting. I never thought about this, and now it came to my mind. Just thank you.
That's true, exactly. So so I mean, ideally, it's just like you said, it has a cost implication. It might, in fact, be hoarding resources that you don't need, and there are a lot of downsides to that one. And the other aspect to look at with HPA is that you can actually use app-specific metrics. So these things that I talked about, requests per second and packets per second, these are Kubernetes objects, and Kubernetes knows them natively. However, you can also specify an app-specific metric, which is known only to your applications. Like, for example, you can create an object called as a external type, and say that the concurrent connections, if the value of the concurrent connections go beyond 1,200, then do a scaling. So Kubernetes can accept this kind of objects as well for horizontal pod autoscaling. However, the problem here is that this has a slight higher overhead from a Kubernetes perspective, and so ideally, the best practice is to try to keep it to Kubernetes known objects as much as possible. But of course, if you have something which makes a lot more sense, then you can definitely go with that. The other one last thing that you need to be aware of from a VPA perspective, from a cluster autoscaling perspective, is that so I think it is the same principle that Jonathan, that you were talking about. So the cluster autoscaler, it is happening at the level of a cluster rather than at the level of a pod. So you can, add additional clusters, but then the problem is when you are trying to downscale. So if you have not set up a pod disruption budget, this can actually cause problems when you're downscaling because it might end up to scaling down to 0, or maybe bring down application pods which you really need. And so you have to ensure that you've set up what is called as a pod disruption budget. And this ensures that how many pods are terminating. I mean, how many while the cluster is coming down, how many of those pods are actually brought down is handled by this particular aspect. So the pod disruption budget. So this is something that you need to have set up so that it doesn't affect your performance as well. So now I just wanted to talk about Cruise. So this is a tool that we've been working on for right sizing and optimizing your containers, and you can use this instead of the vertical pod autoscaler. So the question you might have is why don't I use the vertical pod autoscaler itself? So the vertical pod autoscaler treats all pods as black boxes. It really doesn't know what's inside that box. It can be Node.js or Java, or it can be a database, or any other service that is running. Whereas with Cruise, what we try to do is to peek inside and give you more optimization options. So for example, with Java, we have some special options, which I'll talk about in a minute. And the second part is that we have a Grafana dashboard, which helps you to visualize why we are giving you whatever recommendations that we are giving you. So both of which are not available in the vertical pod autoscaler. So I just want to switch to a demo here. So Cruise is a publicly available GitHub repo. It's there on github.com/cruise/cruise. And the stuff that I'm going to be demoing is all available here, so you can actually try it out on your laptop itself. So what I have running here is a Minikube cluster on my laptop, and I have Prometheus running, and I have Cruise running and Grafana. So what Cruise does is it uses Prometheus to monitor any applications. So in this particular case, I have two applications which are running. So this is Spring Pet Clinic, and this is a Quarkus Prime application. It's a very simple Quarkus application. So I'm using Cruise to monitor these two applications and give me the right size values for what should be the request and limit sizes for essentially for these two applications. And the way that Cruise does it is to use Prometheus to figure out what are these applications, and then it gives me all the information in the Grafana dashboard as well. So now, if you look at, I have this running here already. So this is the dashboard that you can see. So I can choose, for example, whatever namespace and all the applications that are running. As you can see here, there are only two things which are running. So this is the Pet Clinic application. So if I just go back, I think I had it running a while back. So if you see here, so I had applied some load a while back, and this is showing what happened during that time.
Could you make the screen a bit bigger or something?
Yeah.
Because it's not readable.
Okay. I hope this is better.
Yeah. Thank you.
Yeah. So here, this graph represents basically here you can see the green line represents the actual CPU usage, and the dashed lines here represents the recommendation from Cruise. You saw that as soon as I applied some load, the CPU went up really high, and the recommendations also changed because of that. So here you see that the request here is 4.6 CPUs, and the limit is 5.3 based on the kind of spike and actual usage that we saw over a period of time when there was some load running. And similarly, in the case for memory as well, it looks at the size of the heap that it was actually, the total amount of memory that it was using, including the heap plus the native memory. and it comes up with a recommendation for the request as 629 MB and a limit of 1.1 GB. Now, the same thing is represented here as a bar chart. The one thing that you can note here is that, so here, you can use curl, for example. This is a REST endpoint that you can use to figure out which are all the applications that are being monitored by Cruise. And you can see here that it is monitoring Pet Clinic and the Prime, the Quarkus application that I mentioned.
Sorry, Dinakar, but it's not.
Oh, sorry.
Sorry.
Yeah, sorry about that. Okay. So here, the difference that you see is that, for these other applications that it is monitoring, these are some standard, applications that are running inside the Kubernetes cluster itself. For example, Prometheus and Cruise itself. So if you look at these applications, it was not able to find out what was the runtime for that. Whereas for Pet Clinic and for Prime deployment, it found out that the runtime was Java. And so what we can do with that is, something like this. So this is the recommendation. So you can actually, curl this particular endpoint, and you get the recommendations in the form of a JSON, which you can easily convert to YAML and apply it to your deployment. So the way that you can do it is, the information rather that is contained here is the actual amount of requests that you need, the limits that you need, and also the initial RAM percentage and the max RAM percentage that I talked about. This is the best practice. We need to make sure that these are set according to the limits that have been set up here, so that you have the right amount of heap. So what Cruise was doing here was, not only was it reading the amount of CPU and memory that your application was using, but also using Prometheus, figuring out how much of heap and non-heap memory that particular application was using, and based on that, it was able to determine these limits. So it knows how much heap is used out of this particular amount of memory. And so, this is actually equal to here. This is a Unicode character. This is something that we need to fix. So essentially here it is saying that the initial RAM percentage is 45.57 of this particular limit, which is going to be the size of the heap. And because we are setting the initial RAM percentage and max RAM percentage to the same value, as soon as a Java application comes up, you have all of the heap allocated for you. And so, with this combination, you know that you'll get the best possible performance, because this sets aside as much memory as you need and as much CPU as you need. And this one is only for any spikes over and on top of this. And it also sets up the heap size also based on that. So, this is what I would recommend if you're. So you can run Cruise in your cluster essentially and monitor your applications. And one thing that we recommend is that you run it for, let's say, about a week or something like that. So how long should you be monitoring your application? If you monitor it for at least 1 week, you know that it has seen all the kinds of peaks and the regular peaks and troughs. And so it might happen that if you have a holiday sale, this might not work. So you might have to scale. You might have to account for that separately. But at least your regular running of the application is taken care of, with the help of this particular tool. So moving on, the next thing is all about observability. So observability is extremely key. How closely we observe the system and all the metrics associated will actually help us to determine where the performance bottlenecks are and how to go about tuning them. So there are a number of tools out there that can help you to get these metrics. Prometheus, Grafana, and There are other ones that I've mentioned out here as well. Things like Zipkin and Jaeger help you to do tracing, along with, but if you're just looking at the metrics, Graphite and Splunk and things like that can help you with the metrics. I guess the question here is, one of the key things that I have seen is a problem is what should be the granularity of observation. So what happens is that, for example, if you take OpenShift, OpenShift comes with a default granularity of 30 seconds. So essentially, Prometheus is grabbing data off your application every 30 seconds. However, that is actually a problem because you are losing whatever is happening in that 30-second interval. It can have a huge spike for, let's say, about 15 seconds, and you can completely miss that information. So the question here is that there's a trade-off here. So if you try to observe or if you try to grab metrics every 2 seconds, you get very accurate information, but that adds a lot of overhead onto the cluster itself. So that, in fact, might even destabilize the cluster because Prometheus is continuously collecting information every 2 seconds. A lot of applications are running in your cluster, and that causes a lot of network traffic and disk when it is pushing all the logs onto the disk, which might again be on a shared volume, which again causes network and it causes CPU and memory to go up. So there is a trade-off here between accurate information and overhead. So this is something that needs to be well thought out. That for some performance debugging purposes, you might want very accurate information. So you might increase the granularity and make it 1 second or 2 seconds or something like that. But then you have to be aware of the trade-off here, because that might actually cause to destabilize your cluster, and you need to be extremely careful about how you set that granularity. The second thing is it's a very good practice to add additional operational information within your applications. Like, for example, whether it is the MP metrics, Eclipse MP metrics, or the Spring actuator, or Health Center, or some of these tools that can grab additional information. So I showed you the Prometheus logs where I was looking at the heap information. That was possible because in the Quarkus application I turned on MP metrics, and that helps me to get this additional heap information and things like that. So having that information is very key for you to be able to do performance debugging as well. And the other thing here is, so this is something that's applicable only to a private cloud where you have physical access to your hardware. So if I show you the, on my laptop, there are 2 different scaling governors that are running on the operating system. There's something called as a performance and a power save. It has happened to me in the past where on the server, I've seen that the scaling governor has not been set to performance. So if you have set it to power save, that can actually drastically reduce performance. So if you look at what I'm trying to do here is that on my laptop, I have 8 cores, and I'm watching the megahertz values of each of the cores that are running here. So you can see that even though I've set it to performance, it keeps constantly changing, and sometimes, in fact, it drops down. If there's no load running on the system, you see here that it might even drop down to about 1.5 gigahertz. The same thing happens on the server as well, and so you need to be extremely careful not to have set power save, because that can bring down the performance drastically. In fact, I've seen 30% drop in performance just because you've chosen power save. So if you have access to the hardware and you have access to your operating system and hypervisor, this is one thing that you need to make sure that you have set. Otherwise, it can cause a lot of issues and a lot of time trying to debug this problem, which might run into days, and then you figure out that this is what was the issue. Another common issue that I see is with hyperthreading. So the best practice is to not count hyperthreading while you're doing capacity planning, because if you if you have 8 cores, you should ideally plan only for deploying for those 8 cores and not for 16 hyperthreads, because you typically tend to get only about 20% additional performance with the hyperthreads and not full capacity of a core. So you should ideally, the best practice is to not account for hyperthreading while capacity planning. And the last thing that I had was node affinity and pod affinity. So these are additional tools that users have to. So for example, if you're deploying a pod, you can specify a specific node onto which those pods can be deployed to. So this helps match workloads. So for example, if you have a particular pod or a particular application that requires lots of CPU or a high-end CPU, so you can have certain nodes which have high-end CPUs have a specific label attached, so that when you deploy your application, you deploy it only to that particular node, and so you get better performance for that particular application. And the other one is pod affinity, which helps you to schedule related pods together. So you know that there's a lot of dependency and network traffic between related pods of your application, or different microservices of your application itself. So if you can use pod affinity to make sure that all the related microservices of your application are scheduled onto the same node, so that again you get better performance as well. So yeah, I think so. To summarize, make sure that you are producing, optimized container images, which are as small as possible, and they have things like the share class cache or the class data sharing turned on, so that you get better startup and scaling. Do not hard code the heap. Make sure that you use -XX max RAM percentage. And you have to set requests and limits for all application pods, so that you have guaranteed resources for your application. Use app scaling metrics as much as possible for horizontal pod autoscaling. Make sure that there is no disruption of your pod using the pod disruption budget. You can use crews to optimize your runtime. Not only produce the right set of requests and limits, but also JVM tunables as well. And if you have access to the hardware, make sure that you can tune the hardware as well. And of course, last thing is that observability is the key. And there is a trade-off in terms of how accurate the information it provides versus the overhead that it costs. So you need to be careful about that as well. So that's pretty much all I had. And so if there are any questions, I'll take them.
Yeah, thank you very much. It's been a very, very interesting presentation. And well, I think lots of us have been facing some issues of performance in our clusters. So yeah, going back to this presentation as a reference will be more than useful. We have now one question from Alejandro, and
okay,
he can come in and ask the question himself.
Oh, I can read the question if I can make.
Oh, well, no, it's down. It's not in the comments. It's down in the down part where you see questions and answers. But
okay.
Let me stop your sharing.
Yeah.
And well, I don't know.
Oh yeah, I see the question. Okay, I got it. Max RAM percentage equal to n. That's set maximum as a percentage of total memory, but that will automatically be based on the size of the container, or we need to use. Okay, so all the recent Java versions, so starting from Java 8 onwards, have container support turned on by default. So you don't need to use container support. So it comes automatically with that. And So unless you're using a really old version of Java, older than Java 8, you don't need to worry about that. So max RAM percentage is automatically, I mean, I think the default is 80. So actually in OpenJ9, it has 3 defaults. So in the case of OpenJ9, I think what happens is it sets it to 50% for less than 2 gig, and beyond 2 gig, I think it sets it to 75% or something like that. I'm not very sure what happens, what is the default value with hotspot. But I would suggest that you actually do the measurement and set using max RAM percentage. And like I said, you can use Cruise to help you with that as well. And the second question is it worth tuning also the meta space size and limits? Yes, absolutely. So actually we are working on this part where in Cruise we will help you with the meta sizes as well. But as of right now, there's actually a tool that can help you with this. So there's actually a shell script that can sort of gauge the there's a term for that which I'm forgetting. So basically it can gauge the size of your heap and size of each of your meta spaces as well, and give you what are the values for that. But of course, that can only happen at the start of the runtime, so it might not really give you the most accurate information, which is why I think using something like Cruise can help you with that. But then I think the best possible thing would be to look at Prometheus, the logs itself, the metrics associated with that particular application at the end of a run, to see how much of those meta spaces were actually used, and try to use that as the approximation rather than any other value. However, I think one thing that you need to be aware of is not to try and hard code any of these, but to actually try to keep it as a ratio, because that is the most important thing. So one of the reasons why we are talking about using Cruise is because every day you make changes to your application. So whatever worked today might not be the same thing maybe next week, because you added new features. Maybe you need more CPU, maybe you need more memory, or maybe you need less, or whatever it might be. So anytime that you hard code any of these values, you might have a surprise a few weeks down the line, because those values may not match anymore. So this is something that requires constant supervision and monitoring, so that you get the best possible settings. And maybe I can come back to this forum and talk about advanced version of tool that Cruise that we are working on, which will do all of this autonomously, without user intervention as well. But for now, Cruise is what we have, and you can use that to monitor all of these elements as well. Okay, any other questions?
I think there are no more questions. So, Alejandro. Please, Alejandro, I will invite you on the screen. Just accept and ask the question for yourself. It's not take your 3 seconds of fame. I don't know if he's
working, because I accepted.
Okay, now Alejandro, you are there. Ask yourself your question.
Okay. Yes, when you create a new configuration, for Kubernetes, sometimes I had the problem that my pod was continually restarting. So what are your advices to spot the problem? Because maybe because I'm missing knowledge of how Kubernetes is working on the behind, I tend to increase the configuration to, I don't remember the parameter now, but well, about how Kubernetes, checks at the beginning for the loading of your pod. About the resources.
Right. So I think this is a thing that we typically see. I mean, issues with the deployment. So usually, is one of the issues that we see. Out of memory situation where the pod crashes, and the way to debug it is just using kubectl describe logs basically, and describe the pod. Sometimes it might not even succeed in deployment because you might have a wrong configuration, and it might. So, for example, if you look at the kind of problems that you might run into, first thing is you don't have enough resources on any node in the system. So you've set the limits, the request so high that it cannot even be deployed. So how to debug that is to look at describe the nodes. So you say kubectl describe nodes. So for example. Okay, I'm not sharing my screen, but anyway, if you can say kubectl describe nodes, and that will tell you how much memory and CPU are available for use on each node in the system. And the second step is, what is the request and limit for your pod that you asked? And then you can do something like kubectl describe pod for you to figure out that there's a log message that says, resources not available, and it says pending until a resource becomes available. So that's the first problem. The second kind of problem is where you have enough resources to deploy, but then you maybe quickly run out of memory or something like that. And the best way to do that would be kubectl logs to figure out what's happening, or kubectl describe pod as well, where it might give you an information that it was killed, for example. So I think those are probably the most common examples that I can think of.
We have another one, and I will invite Abel to ask it.
Okay.
Abel, are you there?
I'm sorry. I was just checking the camera setup. Yeah, this is kind of a weird question because it's something I've been looking into for some time, and no one is able to give me a proper answer. So if you don't know, just feel free to say that.
That's okay. Yeah.
Yeah. Back in time at a job, we tried to optimize the pods in a different way, because we read some reports that using CDS, the class sharing, the system itself at an operating system level was able to share memory across pods. So for instance, if you have 10 Spring Boot applications, all with the same version, the system was able, and you were preloading the classes, so all the preloaded data could be shared as a virtual memory or a standard operating system shared library. So for instance, if you have 100 megabytes in metaspace, that could be shared. So you could have 10 pods that only use 100 megabytes for metaspace instead of 10 times 100 megabytes, which was 1 gigabyte. And some articles say this can be done, some say it's not, and we never got a real answer.
Okay, actually, I think, I don't know whether this answers your question. Let me see, how can I paste this? I'm just pasting a Stack Overflow link. So this was this was a question that I had answered on Stack Overflow. Basically, I think you're talking about shared libraries within containers and whether there's actually memory sharing happening or not. And so this is, in fact, so I'd done a lot of debugging, and the link there actually tells you what I did to figure this out. And actually, it does work. So basically, the only thing that you need to be aware of is that it depends on the storage driver that is used, which sounds strange, but that's the way that it works. So if, for example, if you're using RHEL 8, which uses the overlay 2 driver, that seems to work. Whereas if I tried with RHEL 7.5, which uses device mapper, it did not work. On Ubuntu, it worked because, again, I think it uses the overlay to FS file system. So essentially, what is happening here is that the physical device, on which let's say the shared class cache or the CDS is residing on, the way that it gets mapped into memory, it depends on the storage driver. So if you have the right kind of storage driver, it maps it. All the 100 instances of your containers are mapped to the same instance on physical disk, and so so there's only one instance of it in physical memory as well, and your virtual memory will just be pointing to that, and so that actually works fine. So it depends on the storage driver that you're using. So that's the answer essentially.
Okay. I mean, that makes sense between all the confusion of the topic. That's something I understand. Then it's more on operating system level, so I could try to test it and reproduce without using Docker.
But I mean, in that Stack Overflow post, I have actually given you the steps about how to find out if it's working or not on your system.
Okay.
So basically, it has a series of steps which can figure out, what is the physical memory for any given virtual memory in any Docker container. How is it? What is the physical memory that it is mapping to? So using that, you can figure that out.
Okay, I will have a look and try it out.
Okay.
Thanks a lot.
Okay. Okay, there's one more question.
Yeah.
Initial delay seconds on how to configure initial delay seconds on the liveness probe. So I guess the question here is, how many seconds is the right value? Is that what is the question? Yes. Okay.
Yeah.
So yeah. So that's it's a good question. I'm not sure there's any universal answer to that one.
We needed to tweak this value in our project from coming from previous versions to newer versions.
Okay.
Because it starts a lot of things. So the initial delay seconds needs to be a lot, because it starts, well, it depends if you are using, I don't know, a big application using Spring Boot, and you also start an EAP image and so on, then you need a longer initial delay seconds, I think.
That's actually a very good problem statement for crews to be able to solve, I think. So actually, I don't think that there's any standard answer as of right now, but based on observation, maybe we can suggest a better value than what you have. So sorry, I don't have an answer to that one, but I think it's probably better monitoring, and yeah, we need to have a better tool, I guess, for that.
Yeah. Thank you. And I think, yeah, this has been everything. So now it's my turn.
Yeah.
Of my 2 minutes of fame. Let's see if I can share my screen now.
Okay.
And yes, I think now you should see my presentation slides.
Yep.
I think so. Right.
Yeah.
Okay. Fine. So for all of you that do not know about the Barcelona JAG, so this is the usual presentation that we give at the beginning of each talk. But we are basically a group of people just following techies. So we are following Java topics, but not only Java topics. And at the moment, we are more than 1,600 members in Meetup. So it's we are very proud of. And yeah, we are obviously non-profit, and we try to invest our spare time, if we have spare time, on the community. Well, we meet and discuss about different technologies. And now it's been the turn of Kubernetes optimization, but well, lately we are doing several talks about Kubernetes. So it could mean that probably Kubernetes is like a trend nowadays. But yeah, not only Java, so different technologies. Here you have all the links that you can use to follow us, but the most important ones are the Meetup one, the Twitter handle, also the YouTube channel, so you can see all our past talks, and even from the conference, so the JVC and Conf, the conference that we do every year. And yeah, in Slack you can connect and share your ideas on Ask about different technologies. Well, these are a bunch of technologies that we have covered in the past, so you can see that there are very diverse, and Quarkus and Spring are not put on the same line just because of anything, just it was random. But we have Kubernetes, AciDoctor, Archilian, well, you name it. Our past events, well, the main one was the JVC and Conf 2019. We had more than 740 attendees, 7 speakers during 3 days and covering different topics. And well, here you can see several pictures of the conference, just in order to have an order of magnitude what it was. And we are expecting to have also the conference on the next July. So yeah, try to follow us and be notified about changes. And yeah, everything is done because of this great group of people just helping.
Okay.
And our next event and the last one for this year is the 2020 Tech Summary Panel. So we are going to have a lot of people from Ana Maria Mihalceano, Andres Almiray, Bruno Borges, Graham Rocher, Heather Vancura, Ivar Grimstad, Josh Long, Mark Little, Oleg Selejev, Shara Chander, Simon Maple, Steve Chin, and Venkat Subrahmanyan, talking about different topics, making a summary of what has been this 2020, a part of the virus, in terms of technology, and trying to cover these 6 topics: Java in the cloud, Java Lang, security, Java platform, present and future of the conferences, and cloud infrastructure. So yeah, don't hesitate to register to this free online event, because I think it's a great opportunity to know about what these main speakers have to say about this 2020. As I said, next 12th and to 14th of July of 2021, we will have JVC and Conf, hopefully. And we need to thank a lot to our sponsor, Jakarta EE, that they are providing the infrastructure, the Crowdcast connection, in order to stream these talks. So thank you very much. And yeah, join us, come to us and ask for events, topics, and if you want to speak, or if you want to have a talk about any topic, we will try to get a speaker for you, or we can make you a speaker if you want to share your knowledge. And this event was about optimizing application performance on Kubernetes by Dinakar Guniguntala, is architect and in runtime optimization for cloud at Red Hat. He has come from IBM previously,
yep.
And well, official maintainer of AdoptOpenJDK Docker Images. So yeah, it's a good person to follow about all the technology topics that he can share. And that's been everything from my side. So thank you very much. And don't forget, if you have some minutes, I know it's super late for you, Dinakar, but if you want to share some minutes, we are going to go to our virtual reality island, in a few minutes. bit.ly/BarcelonaJackBR. You can you can join us with your browser, your phone, or your VR glasses, and we can chat a bit about whatever.
Oh, great! Yeah, I can do that.
Okay, thank you very much, everyone, and I hope you have enjoyed this event. And I expect to see you soon. If not, have a very nice end of the year. If you follow Christmas, Merry Christmas. If you follow any other approach, happy whatever. But in any case, have a good end of the year, and hopefully we will start better this next 2021. See you soon. Thank you very much.
Yeah.
Thank
Gracias.
you. Thank you.
Okay.
Bye.